introduce now Silke Weinfurtner from the University of Nottingham. She will talk about out of equilibrium hydrodynamics rotating black holes. Thank you. Silke, I cannot hear you.
Classic mistake. I didn't unmute. Okay, so I'll start again.
Okay, great.
Thank you,
yes,
organizer, for your invitation. I'm going to talk about hydrodynamic black holes, or the effort to set up black hole processes in a controlled laboratory environment. And in particular, I'm going to focus on out of equilibrium. I'm going to explain what I mean by that, out of equilibrium rotating black holes. Okay, let's, okay, computer is a bit stuck, but it's working now. Okay, so I'm going to, just for some people, perhaps most of you have heard about analog or hydrodynamic black holes, but I'd like to just motivate it a bit further. So what I'm interested in is field theory on curved spacetimes. And there is a simple way of understanding sort of the basic of how we do field theory on curved spacetimes and how this connects to systems different than gravitational systems, or how this connects to these analog gravity systems. So I have a very simple equation here. This is a second order linear partial differential equation. It is used a lot in classical physics, for example, to describe material waves, sound waves, for example, or also for light waves. So we encountered this in many forms throughout studying physics. Now, there is a trick to rewrite that equation, for example, by considering this constant c here being the speed of light, for example. I can rewrite that equation in a compact way by introducing flat spacetime or the Minkowski spacetime. So it's the same, these two equations really are the same. It's just a different way of writing. So why is that handy? Because if you are looking at wave propagation, right, on a homogeneous background, or if you look at wave propagation or scalar field propagation on flat spacetime, there's a very reasonable way of how to extend that from flat to curved spacetimes. And that is simply by saying, well, if it's not coupling that field to the flat spacetime geometry, let me just ad hoc replace my eta AB, representing the Minkowski spacetime, with the general GAB, representing a general curved spacetime geometry. And then you can put in whatever you want to, for example, consider how the scalar field behaves around a black hole. Now, the reason why I'm explaining this in great detail is because we have constructed this theory more or less ad hoc, and it's a very reasonable way to do it. But there are actual examples where this works, where this comes out naturally. And this is what this talk is about, as one can say, a variety or broad class of laboratory systems. They are dubbed as analog gravity systems, most commonly. And what these systems, very different systems, optical systems, fluids, superfluids, what they have in common is, if you look at small fluctuations within, they experience an effective classical or quantum field theory in general curved spacetime geometry, an effective spacetime geometry. And now I quickly want to explain what that means. So if I look at the small equations, there is, I can find a parameter space where this equation, the fluctuations, are governed by a dynamical equation, which is exactly the same as I introduced to do field theory in curved spacetime. And what is beautiful about these analogues is that this ad hoc replacement is actually built in. And what I mean with this, if you have a general fluid flow with a background velocity and an inhomogeneous media, you would have to use or introduce a GIB, a general curved spacetime geometry. If you switch off the background flow, and choose a condensate, a medium, a homogeneous medium, this GIB reduces to a Minkowski spacetime geometry. So here it really works in the way we think about classical and quantum field theory in curved spacetime. Classical or quantum is a matter of choice, depending which media you're choosing. If you're using a classical fluid flow, clearly you're doing field theory on a classical background. If you're using a superfluid flow, a superfluid, ultra cold gas of atoms, then your perturbations require quantum field theory, and you end up with a quantum field theory in curved spacetime. So this is this analogy. It's a simplification, but it creates a link, and this link is the effective field theories of how we constructed it for quantum field theory in curved spacetime, and the effective field theory that you automatically get in these systems. So all of this talk is about studying and learning about effective field theories. Okay, so we have an effective field theory, which is of the sort we would like to have it, and now we want to get a particular spacetime geometry. And the one I'm interested in is a rotating black hole geometry. The reason why rotating black holes from a quantum field theory or classical field theory point of view are so interesting is because they have beautiful or fascinating geometrical properties. They have apparent event horizons, ergo surfaces, light rings, and so on. And what's important for field theory in curved spacetimes, each of these geometrical features gives you an effect to probe. So the apparent horizon links to Hawking radiation. If you have ergo surfaces, that links to superradiance. If you get light rings, you get ringdown. So this is the reason why we're focusing on rotating black holes, because there's so much physics that can be explored in a controlled laboratory system. So what is the medium I'm using? So to start with, I'm going to focus on surface waves. And what a surface wave is a two-fluid system. So the one we encounter in the ocean would be the one fluid being the water, and the second fluid would be the air above. And the interface between these two fluids that don't mix, that gives me a two-dimensional sheet. And what you can show is that surface waves propagating on this interface, they experience an effective 2 + 1-dimensional spacetime geometry. And then there are various approximations, assuming that I have really a 2-dimensional fluid flow. So I'm in the shallow water approximation. So I have a velocity profile, which in cylindrical coordinates has a radial and an azimuthal component, an angular component. So this is the setup, a 2 + 1-dimensional effective field theory, or a field theory on a 2 + 1-dimensional analog curved spacetime geometry. And this vortex flow, they exhibit analog rotating black hole geometries. And going to very roughly, just to give an intuition, is how it shares some of the features we are interested in around when it comes to rotating black holes. So I have the word event horizon here, which I shouldn't. It should actually be apparent horizon. So let's start with going through this and focus on this apparent horizon. Now you have a propagation speed, and I'm looking at surface waves, which has a very long wavelengths compared to the depths of the water. And those are the shallow water waves. And their velocity scales with the height of the fluid. And what you can see is that if you have a radial flow, where you have a radial flow and an angular velocity component. But if I'm now only focusing on the radial part, the apparent horizon, or analog event horizon, let's live with this for now, is where the radial velocity is equal to the propagation speed of your surface waves. For the ergo surface, you also take into account the angular velocity field. So when the total radial and angular velocity is exceeding the propagation speed, you get an ergo surface. And as it will show, you can also get light rings, which are further outside. And each one of these effects, each one of these horizons should lead to some physical, to some observable consequences. Right, so how do we set this up? This was the experiment. It's really a very classical experiment. I'm using 2 tons of water. It's, again, here, this green, little green glowing fluid here is the water. I'm looking at this interface here between air and water. We are setting up, in order to get a radial and an angular velocity field, which is increasing towards the center. I put a little plug or a drain hole in the middle. And then what you have, you feed in the fluid flow in a way that it gives it angular momentum. So the drain allows you to have a radial component, and the way you feed in the water gives you an angular fluid component. Now, from a field theory perspective, what we're interested in, or our observable, is the free surface. So what we need to do, we need to map out this free surface as a function of time. In the time domain, we need to follow all the little fluctuations and ripples that occur on this interface. In order to do this, you put some fluorescent sodium salt into the water. And what this, once dissolved, what that does, if you shine blue light onto that free surface, it converts it into green. And so what it allows you is to actually see the boundary of that fluid, because water is transparent, which is why we need to do this. But it also allows you to take out direct reflection, because you can only look for the green light and filter out the blue. And then what you need to do is you need to set up a detection method we're using here is simply to we have 2 cameras here on the right and the left that takes 800 pictures a second. So we do stereo imaging of this free surface. In the middle, we project a blue pattern, a random blue pattern onto the free surface. Knowing what the pattern is and taking doing stereo imaging of the deformed pattern, you can use correlation methods to reconstruct this free surface. Okay, now let's first look at the whole idea is we want to study the effective field theory. And what that means, I want to study how waves interact with these vortex flows and how many of the features we are expecting to occur around rotating black holes can I actually see in the lab. And what I would like to focus on as a first thing, I want to just study this wave propagation on this effective curved spacetime geometry. So what you're seeing here, this is data taken from this experiment. And I will start the video soon, but what you're going to see here is a wavefront propagating towards that vortex core and is interacting with it. And as a consequence, because it's propagating on an effective curved spacetime geometry, it gets deflected. Okay, so let's just look at this. So these waves, they interact with this vortex in the center. And the first thing we wanted to study is, or not the first thing, that experiment was built to look for superradiance. But after that, we wanted to understand how this wave pattern comes about and how is it linked to light bending. So what the video I've shown is data recorded from the experiment, but we did some filtering. Because if you have a stationary fluid flow and you send in a coherent wave at this fixed frequency and it's stationary, the frequency won't change. So what you can do, you can filter out for a single frequency band. And what you can do, you can stimulate that system with different frequencies. And so what you see here are snapshots from A to F is just different frequencies, waves, coherent waves with different frequencies interacting with this vortex flow. And the question is, can we understand this deflection behind as geodesic motion in the system? And I have to say something here. When I established this analogy, I had this very simple equation. Now, thankfully, these analogues are not, the analogy is not that deep. And this is a great virtue here because it allows you to test for robustness and universality of these processes, in the sense that what if your field theory is much more complicated? Can you still extract all these wonderful features which you derived with a very simple, starting from a very simple effective field theory? And so what this effective field theory here is really, just to remind ourselves again, we have two fluids. In my experiments, it's air on the top and water on the bottom. We are now also working with two fluid systems. And the reason for that is if you want to get high precision measurements, you need a closed system. So I have an open system, and in a way that shows, if you do high precision measurements of free surfaces, that the water will be evaporating. So for anything ultra precise measurements, where you buckle down to nanometers of measurements of this free surface, which are possible, you need to work with closed system. But the kind of experiments I'm talking about now, you get away with less. So we have this two fluid interface, one fluid being on top, one fluid on the bottom. And this is a complicated interface, the equations, to derive these equations, you start with two coupled Navier-Stokes equations, and you make many approximations. And what I'm saying is, even after many approximations, what you get a dispersive field theory. So it's not that simple. It's not a second order field theory either. So to make precise prediction is actually an art, and you have to take the modeling for developed for black holes to derive, for example, quasi-normal modes. You need to adapt them to this specific effective field theory. And I don't want to go into the details, but what we are doing here for the first theory experiment match, we are solving the whole wave equations using ray tracing methods. And we get a set of Hamiltonian's equation, which we then solve numerically. And this one here is one of these results. It's a very simple one, but I really love it. It was just meant as a first test, but it demonstrates something really beautiful, which is how curved is this spacetime for this coherent wavefront. I have a single wavefront now, which is moving towards my vortex. And this shows very nicely how these two waves, that the wavefront that's coming towards the upper part is counter-rotating and core-rotating, depending on where you are, that the wavefront interferes with itself. And this is due to this effective spacetime geometry. Right, you can now say, look, we have done this experiment. We know what the fluid parameters are. I'm assuming a rotational flow, meaning I need a single parameter to characterize the radial and the angular component. This is a good approximation outside the rotational core of the vortex flow. It is, per definition, a very bad description inside the rotational core. But outside, this is a very good approximation. We know what the water depths are, we know what the wave number and the frequency are. And from this, we can then run our simulations, and we can make a prediction of how the geodesic, or perhaps more accurate here for dispersive field theory, the characteristic motion in the system works. And you can predict how these wavefronts will look like after interacting with this vortex flow. And we can then superimpose an experimental result with the theoretical prediction. And now this is a very crude way of comparing theory with experiment, but what it shows is that it's not too far off. It shouldn't be a correct match, because in the approximation we are used, we should be more or less in the adiabatic regime, which meaning that given that in this experiment superradiance takes place, that there's actually an exchange of angular momentum from the vortex flow to the waves. We did never expect a precise match. And also this is not a way to do a precise match. But just what this told us is that the characteristics we have a good handle on the theoretical understanding of wave propagation outside that vortex core. And with this, you can calculate what is here indicated with black circles here. You can calculate these light rings. And these light rings, and this is what I'm going to talk about now, are really important because once you have these light rings, you can calculate the black hole ringdowns, the characteristic frequencies which a perturbed hydrodynamic black hole should give off. And so if you want to venture into the non-equilibrium, one way to do it is to, just as in the black hole case, focus on an effect that you can still describe with perturbative method, but which is the outcome of a highly non-equilibrium process. What is really beautiful, this is the beauty about it. So in these ringdown modes, they probe the newly formed black hole after following a black hole merger. And which ones are getting excited is a matter of the dynamical process. But in which frequencies and what are the decay rates, that doesn't depend on the dynamics. That only depends on the final state. So if you want to study hydrodynamic black holes and push them into the non-equilibrium, you can start by getting just a little bit away from the equilibrium, and then you can see how much you can push it and what is changing. Okay, so I think all of you know this very much, so I don't need to say much about this, but just to be clear, so what these light rings or circular orbits are, they're boundaries of things that can escape and things that fall inside. And depending if you're core or counter-rotating to this rotating black hole, you get a different light ring. So there is a counter-rotating light ring that sits very much outside, far outside. And they are the core rotating light rings that sit very much inside. And in fact, in our experiment, they would sit inside the rotational vortex core. And we have some theoretical models to deal with it. But we have conflicting theoretical models, and our experimental methods fail to actually investigate that, at least at the moment. However, the outer light ring is a robust concept which sits within the irrotational part of the fluid flow. And this, once you have these light rings, you can calculate it, the ringdown modes. And the ringdown modes has a real part linked to the circular orbits, and it has an imaginary part, which is linked to the boundary conditions in the system. And so you have to understand that what we are doing in any of the analog gravity experiments, we're doing field theory or quantum field theory in a box. We put a black hole and we put it in a box. And the boundary conditions are very hard to control. So in our case, we'll have a lot of reflection back from the boundaries. So we don't have open boundary conditions. And so this means that we do not expect to see this nice exponential decay. So these ringdown modes, the real part should be robust. And there was also something to test, does it depend on the boundary condition? And within our measurements, it doesn't. So how does this look like? This is a simulations in the time domain for a non-dispersive wave equation. But this is how it would look like. You could stimulate them by having a train of waves passing by. And when the wave's gone, what you see is left behind is the spiral waves. This is one way of exciting them by sending, for example, a wave package or some continuous signal that stops. Now, the problem with doing it this way, we tried very hard, is that if you send a wave packet, we have a wave machine that, for example, can generate Gaussian wave packets. If you send that against this analog rotating black hole, you inject a lot of noise in the system. Now we have a black hole in a box. Eventually these waves propagate to the boundaries and come back in. And so this is not a good tool to really measure that. So we had to think a bit outside the box, or within the box, perhaps, in this case. And what we did is we said, okay, all we need to do is give this vortex flow a hard time. So what we did, we let it go to a stationary state, and then we overfilled it and let it settle back to the stationary state. And what we saw, and something which we noticed already before, when you look at vortex flow in the bathtub, wherever, what you see is there's a constantly waves being given off, and these waves, they are counter-rotating waves. And this is one of the signals. Counter-rotating waves means if I have quasi-normal modes being given off related to the counter-rotating light rings, these are counter-rotating modes. And so this is what one sees by eye, and this is how a typical surface looks here from our experimental realization. And what we are plotting here is for different azimuthal modes in the system, counter-rotating azimuthal modes. Here, for example, m equal -10. We look at the power spectral density over r, over the radius. And what we plot here is a theory curve, which is this red one. And this red curve is, if you are in a particular distance from the center, this curve tells you what your minimum energy needs to be in order to be still an oscillating mode and not an evanescent mode. And that means is if a wave is below, comes in and is hitting this red curve, it means it can't propagate further. And so this, you can think of it, it's not that simple, but as an angular momentum barrier, this rotating black hole creates through this effective potential outside, and the wave can't propagate past that. And the light rings, and you can show that mathematically, they are the maximum on that red curve. So this is the minimum energy needed that a wave can propagate from the boundary, from the outside to the inside of the black hole, or to the core, vortex core. These are the light rings, and they should have a constant frequency. And this white dashed line is showing you the maximum of this red curve, and that's where the light ring sits. So from this power spectral densities, we see directly that we get these light ring frequencies. And you can then, and this is not the main part of this talk, but what you can do, of course, you want to say, I have an effective field theory that predicts some light ring modes. And I can take fluid parameters, put them in and make a prediction. That prediction would be on this right plot here, where I'm plotting the frequency over the azimuthal number. The black line would be the prediction. The green dots with the error bars is what we get by just looking at the free surface and do some data analysis to extract these light ring modes. So they match. You can also do a reversing. You can ask yourself, what if I can't measure that fluid flow? Can I use these light ring modes? And knowing what my effective field theory is, can I use it to determine the fluid parameters? And the answer is yes and no. It depends. It's a bit more convoluted, but in principle, yes, it is possible. Right. And so there are a few things which were very surprising. And the first one was, and this was a big question, we knew how to calculate it. We wanted to know if we have a good grasp on the effective field theory, but we weren't sure if it's easy or hard to excite these modes and how many are excited. And if you look at the plot, they are heavily excited. So these modes, you have to think of them channels that open. And if a system is out of equilibrium, it needs to use this channel. This is the first channel it can use to actually shovel energy from the center to the outside. So what we see naturally in all of these analog systems, these channels have to be used, and this, or it makes sense, it's reasonable. And what this experiment confirms is, yes, indeed, they are being excited. It's an easy experiment to do in a way. So, right. What we also see now, and which we investigate, you can go further from this quasi-equilibrium, and you see already counter-rotating modes, and it becomes an exercise now to see around which background you have to perturb, which is matching the experimental results. But you already see that you can push further away from this equilibrium, and you still should have a good description. And this puts me to my next part. Stefano, how much time do I have?
Well, you miss 1 minute and 50 seconds to make 30 minutes, and then you would have other 5 minutes. So let's say that you have roughly 6 minutes.
Okay.
Something.
So the next thing I want to talk about is back reaction. And I'm saying, okay, so back reaction is sort of a glorified effect when it comes to quantum field theory, and it's because it's related to black hole evaporation. Because when a black hole, when a star collapsed and formed a black hole, it can only reduce its mass by giving off this Hawking radiation. And this Hawking radiation is carrying away the mass of the black hole, so it can evaporate. So Hawking radiation is ultimately intertwined with the back reaction process. And for these analog gravity systems, there was an issue here. There was always believed that, well, hydrodynamical black holes are externally driven systems, meaning while we set up a fluid flow, or we move some obstacles through the flow, or some laser field as Jeff does. And so therefore, how much back reaction can you really expect, since sort of you are driving this? It's not like a black hole that has a mass and it's evaporating it away. And so what is really needed as a first step, and many people say, well, it would be wonderful to use this system to study this and see how a back reaction effect would, for example, manifest itself in Hawking radiation. But the problem here is a much more deeper one. Can we actually have involving hydrodynamic black holes in a laboratory system, given that they're driven? And in principle, the general, consensus in the community was, no, you can't. You might have a tiny modification, but really no. And what we saw in our experiments was the opposite. So when we had this experiment here where we looked at the waves interacting with the vortex flow, we had to do these experiments very quick. We had to start the wave, so the wave was filling our sensor, the field, but then we did immediately the experiment and we stopped. And the reason was because we saw that the water height was running away. It drained more. And we just said, okay, we need to find a way around it. And at some point we need to figure out why that is. And this is what we did in this paper, recently published in 2021, with Sam Patrick, Harry Goodhue, and Silke Weinfurtner. We looked at these experiments again. And what we found is that, and something Harry said, which I thought was really true, he said, well, when you have a black hole, for example, right, and you throw something inside, the mass of this black hole is growing. Now here, if I throw something inside that analog black hole, it just drains and leaves the system. There's nothing can accumulate. It's not quite true, as it turns out, because surface waves, when you send them around, if you take in your bathtub, you send off a little wave, that wave carries a little mass flux with it. The reason why it doesn't matter in the bath is because the mass fluxes will not magically pile up in one corner. They will, equilibrate again to a flat surface. But if you stack a horizon into a fluid flow, you're creating a one-way membrane. And so this mass fluxes, they can actually drain the system. They can reduce the mass of the system. They could increase the mass of the system if you play with these mass fluxes in the system. And as it turns out, you can predict by calculating the back action of your perturbation onto your background flow. And what we predicted is that as a consequence, the water height should decrease. And the way you can do it, you run a scattering process. You can calculate how much you send in and how much goes back. What's missing has been drained. And you can then calculate from the wave effect how this back reaction effect should manifest itself. And the surprising bit here is that what we did to do this, we're assuming a slowly evolving, or we're using a static space-time geometry. And what you're seeing is that we expect this is the water height as a function of time. And what we expect is that the water height is going down. And we see this linear slope. We see that it has all the characteristics we wanted it to have. It doesn't scale much with the frequency. But what is really remarkable here is that the change in the water height, when you start from 10 centimeter, it's linear up, the change being linear, and then it becomes non-linear, this curve, the water height, meaning that some other physics kicks in. But as long as in this linear regime, it actually is the back reaction by assuming a curved space-time geometry where you're still within just the next order correction. And what you see is that you can drain the water by 1.5 centimeters. This is significant, this is huge. And what you can argue here is now that you have, following the same techniques people use if you have a slow time dependence in a space-time geometry, you can work with the Born-Oppenheimer approximation for slowly evolving backgrounds. And what it shows that this analogy still holds for slowly evolving backgrounds. And here, by changing the water height, you change the effective mass of the black hole. And in a way, you can say, similar as in a black hole, when a black hole evaporates, right? It gives away, there are two ways to measure if a black hole evaporates. you can say, or undergoes a Hawking process. You could measure the radiation given off from the black hole, or you could measure the mass of the black hole. And the mass of the black hole keeps track of how much radiation has been sent off. And in this sense, the water height, which is the total mass of the system, has a memory, and it memorizes how much, it memorizes the scattering process in the system. And there you have it now. You have a system that can undergo Hawking radiation, and you can have a back action to the zero mode, to the background. And I believe that all analog gravity systems are intrinsically back reacting. You just need to look carefully enough. And I think I'm at the end of my talk. Otherwise, I would use 3 more minutes to talk about ringdown in quantum systems. But Stefano, you're in charge, and I can just stop equally well here.
Okay, in principle, you have 30 seconds. If you can give in 2 minutes.
So what is the next? Okay, so now you made a mistake because you let me carry on. But anyway, so here's the thing. This is all known physics. So how can we push this into something which we do not understand so much? So the way to go forward is to turn this experiment into a quantum experiment. And what I mean with this is, as a first step, I want to turn the angular momentum into a quantized. I want to quantize the angular momentum. I want to quantize the circulation of my hydrodynamic black hole. The way to do it is to replace the fluid with the superfluid. The superfluid of my choice is superfluid helium-4. And automatically, by going to this, it means you need to make a call. You need to work with a different fluid. You need to cool it down below 2.7 Kelvin, and you need to make it smaller for many reasons. One is that you can cool it down, and helium is very expensive. So you need to reduce the volume considerably. So from 2,000 liters to 10 liters of superfluid. And then if you really want to then have a discrete angular momentum, which I would dub as a quantum feature of a black hole, and you want to also have a quantum field theory interacting with the system, you need to go one step further. You need to make it smaller and colder. And the reason is because you need to reduce all the thermal noise in the system so that the quantum noise in the system is dominant. And then you have a quantum field theory interacting with an effective black hole that exhibits discrete circulation. Goal is clear. We're going from classical gigantic fluid flow to macroscopic superfluid helium flow, few liters, and then we go to nanoscales, and this the last step will take place at the University of Royal Holloway. And we did a bit of a ringdown experiment using a simulation for 2-dimensional Bose-Einstein condensates. And what you see is a vortex cluster that contains 29 topological vortices. So a vortex in a superfluid is quantized, it's topological. There is an irrotational fluid flow. So you get this, and when you want to put a vortex with a higher winding number together, it will decay into individual vortices. What we do, we stack up these vortices 29 very closely together, and then we see them decaying. And what we are doing, we're stacking them close enough so that they exhibit a common light ring. And the moment they exhibit a common light ring, I can forget about the microstructure of this fluid flow. And I can use a coarse-grained velocity field to describe the whole scattering process. And this is how it looks like. So the vortices are rotating. The white one is the ergo surface. The green one is the light ring. And what you see is you see all this noise being given off. And these modes, just as we show, as long as these vortices are within this green line, all of these fluctuations you see, the spectrum can be fully characterized through a coarse-grained vortex flow. And we're using all the black hole methods. And what we see that this noise you're seeing here, which is counter-rotating, is indeed this light ring mode. So we identify the different stages here, and we show when the microphysics can be forgotten. And this is the feature that's important here, is this light ring. And so you can then also predict the frequency for the different azimuthal numbers. The black dashed line is the prediction, and then we pull out, here's our spectrum from the simulation on the right-hand side. and we focus in on one or few of these white lines, and we plot these violin plots, which clearly shows that these frequencies are excited in the system, right? And you can really predict the whole spectrum. So you found a way to describe a disordered vortex lattice using perturbation theory. And how does this look like? So we started the experimental implementation, not for ultra-cold atom system, but for superfluid helium. Last slide, Stefano. This is the new lab. We started in July this year. We want to set up a stable superfluid vortex flors at ultra-cold temperatures. The experiment is here in the middle. We are now working with interferometric detection methods to implement global and local observers. Local observers can be thought as particle detectors in the system. Wrote a paper about that with Bill Unruh, Jörg Schmidmeier, and Jorma Loko. And the interferometric techniques, they need to be set in a clean room environment, hence this box here. And so, and then of course, the challenge is to bring these observers together with the new quantum system. So we have to set up a hybrid superfluid optomechanical system, and that's the goal. And who is we? And then I really stop. We, that is a large collaboration in the UK. 15 collaborators in the UK with 6-7 external partners, and we are have formed teams. We're working on one part is working on focusing on the false vacuum decay and connection to cosmology, and the other part is working on this quantum black hole simulators. And so we are a very multidisciplinary bunch of people which are working together, and our network initiative is called Quantum Simulators for Fundamental Physics. And I'm apologizing for being late. Thank you.
Thank you. Thank you. I think that at this point we have time for one question, then we will stop for 10 minutes and have the discussion. So I see that there was a question, well, several questions by Deepak Vahid. I will give him the possibility to speak for one question. So pick up one and the rest can be talked in the discussion.
That's a nice question. So, and in fact, that's something we're looking into this. So the question was, can you generate angular momentum also by having an angular asymmetry in the drain? Wonderful question. So if you have an can't say. If your drain is not, yeah, thank you. Asymmetry, yes. If your drain is that, then what it means is, so in every plot I always talked about azimuthal numbers, and this is because of the symmetry of the fluid flow. Because what you're doing, you're having a theta component, and you do a Fourier transform to the azimuthal number m. This you can only do, this nice replacement, if the background flow doesn't depend on theta. If it depends on theta, you can actually couple different m modes together. This is one thing which I'm particularly interested in implementing, because what happens, for example, if your wave equation for a black hole is non-separable? And it would be nice to see if we can still do some modeling and see what happens to ringdown process or superradiance, what happens to these processes when you break that feature, which seems to be a built-in feature for black holes, that they have separable wave equation. So this is not spinning up the fluid. It makes effective field theory hard, which is good. It's an interesting, no, it's not what, it is interesting, but not to spin up the fluid flow.
Okay, great. So let's now have a stop for 10 minutes